In this video, I will demonstrate the functionalities of NumCPP that were implemented for you. I will also explain what is happening inside some of the functions that are being called by each matrix instance. First, let's look at the matrix class. First, we create two matrix instances containing integers, matrix 1, matrix 2, followed by a matrix instance containing doubles. We also try to create a matrix instance where all of the rows are not the same length, as shown by this error message that says error, invalid dimensions for matrix, setting matrix to empty. Now let's look at the overloaded operators that can work with matrix instances. The ones we will be using to help demonstrate this are matrix 1 and matrix 2, which are represented here. Here we have the element-wise sums, differences, products, quotients, and remainders. Then, we test the overloaded logical operators. None of the elements in matrix 1 and matrix 2 are equal, so the double equal sign result consists entirely of zeros, and the not equal result consists entirely of ones. All of the elements in matrix 1 are less than those in matrix 2, so the greater than result consists entirely of zeros, and the less than result consists entirely of ones. Same with the greater than or equal to and less than or equal to results respectively. Finally, we demonstrate that arithmetic cannot be performed on matrices of Boolean values, and that Boolean values are represented by zeros and ones, meaning false and true, in the context of this project. Now let's look at the array creation functionalities that were implemented. We have the empty function, which fills an array with garbage values based on what data type is specified by the user. The I function places ones on the diagonal based on the value specified for the diagonal by the user, and zeros elsewhere. The identity function creates a square matrix, meaning the numbers of rows and columns are equal, with ones on the diagonal and zeros elsewhere, with the diagonal value being set equal to 0. The ones, zeros, and full functions fill a matrix with ones, zeros, or a user specified value respectively. The ones like, zeros like, and fulls like functions do the same thing, but end up creating a matrix instance with the same row and column counts as the instances specified by the user. The NumCPP function, which is represented here, serves as an alias for the matrix class's regular constructor. The loadtxt function, which was demonstrated by this matrix instance named fileIntMatrix, opens a .txt file and loads its data into a matrix instance, while along the way ignoring special elements such as comments. Here you can see the .txt file that was just read in. It ignored the comment, and it read in all of the comma-separated values. The aRange function creates a set of numbers that are evenly spaced based on the start and end values, as well as the step value, all of which are specified by the user. The linspace function does the same thing, but the number of steps is determined by the user instead of the step value. The logspace function behaves the same as the linspace function, except all the numbers are evenly spaced on a log scale. Same with the geomSpace function, but the numbers are evenly spaced based on a geometric sequence. The diag function returns all of the numbers that are on the user-specified diagonal of a matrix, as shown by these three instances here: diag test 2, 3, and 4, 0, 4, 8, 1, 5, and 3, 7. The try function creates a matrix with 1s on and below the user-specified diagonal, as represented here, and 0s elsewhere. Now let's look at the array manipulation functions. First, we use the copy_to function to copy the contents of one matrix instance to another. Just make sure that the dimensions of the matrices are the same. As shown right here, A now contains the elements of B, and C now contains the elements of D. The shape function returns a vector, with the first element being the number of rows, and the second element being the number of columns. The flatten function basically stores all of the matrix instances data inside a single vector. The transpose function swaps all the matrix instances rows and columns. On top of this, we can use the concatenate, hstack, vstack, column stack, and row stack functions to combine matrix instances along a specific axis. If the axis is 0, then we are concatenating along the rows. If the axis is 1, then we are concatenating along the columns. Otherwise, we simply combine all the instances data into a single vector using the flatten function that was described earlier. This will come up again for some of the other functions that involve working with certain axes of a matrix. So remember that for all the matrix instances that contain either axis 0, axis 1, or axis -1 in their name. We use the unique function to determine the indices of all the first instances in which each unique element appears. In this case, 1 first appears at 0, 2 first appears at 1, 3 first appears at index 3, 4 first appears at index 6, and so on and so forth. We can also use the unique function to return all the elements of a matrix with duplicates removed. We can also use the trim zeros function to remove all the zeros from the back and or front of a vector based on what the user specifies. We use the flip function, as the name implies, flip the elements of a matrix over a specified axis, using the same axis rules that were described for the concatenation functions. We could then use the save as CSV function to store the contents of a matrix instance, as shown here by the save as test instance, in a CSV file like this. As you can see, I just created a CSV file named matrix test that contains the data in that save as test instance that the save as CSV function was using earlier. We use the repeat function to repeat the elements of a matrix either row-wise, column-wise, or element-wise. We use the delete function to delete the elements of a matrix, once again, either row-wise, column-wise, or element-wise. We can also use the append function to append elements to a matrix using the same access rules that were described once again back when I was explaining the concatenation functions. And finally, we can use the insert function to insert elements into a matrix, either filling an entire new row, column, or by a single index with a user-specified element based on the access value. Now, let's turn our attention to logical functions. First, we demonstrate the wrapper functions for all the overloaded logical and element-wise comparison operators, such as XOR, AND, OR, and NOT. And the greater than or equal to, less than, and less than or equal to, and not equal to operations. We can also use functions that test each element of a matrix to see if they meet certain criteria, such as if they are finite, meaning that they are neither infinity nor not a number, or if they're infinite, meaning that they're either positive or negative infinity, they're not a number, or if they're negative infinity or positive infinity. Let's now look at the mathematical functions. We can compute both the sum and products of matrices using the access rules that were described back when I was demonstrating the concatenation functions. We can also do this while ignoring not a number values by converting them to 0 and 1 and for addition and multiplication respectively, as shown by all these statements that include ignoring NaNs. On top of this, we can compute the cumulative sums and products, also using the access rules for a matrix, and also while using the same rules that were just described for not a number values. We can perform exponential operations on matrices, such as the natural exponential function, or raise 2 to the power of each element. We can also simply subtract 1 from the element y's results using the natural exponential function. We can use the natural log, log base 2, and log base 10. We can also compute the greatest common divisor and the least common multiple of the matrix. On top of this, we can perform trigonometric operations on matrices, such as sine, cosine, and tangent. The sine and cosine functions use the respective power series for each measurement, with the number of iterations and decimal places being specified by the user. Tangent is just sine divided by cosine. And some of the other trigonometric functions we could perform are arcsine, arccosine, arctangent. We can also perform sine h, cosine h, tangent h, arcsine h, arccosine h, and arctan h. I do not want to go into much detail on these due to time constraints, and also because I do not want to overwhelm you with too much information about trigonometry. In addition to trigonometry, we can also perform linear algebra operations using NumCPP. We could compute the inner product of two matrices. which is done by adding together the element-wise products of the matrices, like we're doing here. We can compute their outer product, which results in a matrix with each column equal to multiplying each row of a matrix by the corresponding column in the second matrix, as also shown here. We can also compute their regular product, which contains the same number of rows as the first matrix and the same number of columns as the second matrix. The dot product of two matrices can vary based on their dimensions. If they are both two-dimensional, meaning that if at least one of the matrices is two-dimensional, meaning that their number of rows is greater than 1, then the dot product is simply the matrix product. Otherwise, if both matrices are one-dimensional, meaning that they both only contain one row, then the dot product is just the inner product. We can compute the eigenvalues of a square matrix, meaning that both the row and column counts are equal, when provided with a vector, with both being represented as instances of the matrix class. For example, let's consider eigenvalue test 1 and eigenvalue test 2. We obtain their regular matrix product, and then compute the greatest common divisor of the product matrix's elements. In this case, we end up with an eigenvalue of 4, which satisfies the equation that is being described here. Therefore, our return value ends up being a pair, with the first value being 4, and the second value being a Boolean value of 1, meaning true, meaning that it satisfies the equation for eigenvalues. This is also what's happening with eigenvalue test 3 and eigenvalue test 4. We can also compute the determinant of a matrix like we are doing here, which simply put for a square matrix with 2 rows and 2 columns is A times D minus B times C. We can also compute the row-reduced echelon form of a matrix, which can be useful for when we want to solve a system of equations. Let's consider RREF test 1, for example. The system of equations being represented here is 2x plus 4y minus 4z equals 6, 2x plus 6y plus 4z equals 0, x plus y plus 2z, equals minus 2. The solution for this is x equals -1, y equals -1, and z equals -1, which is being represented here by the row-reduced echelon form of the matrix. This is also what's happening with RREF test 2 and RREF test 3 here. We can raise a square matrix to the nth power, which is specified by the user, by performing matrix multiplication a specific number of times. So we can raise it either to the second power or to the third power, for instance. And finally, we can compute the inverse of a square matrix by concatenating it and its corresponding identity matrix along axis 1, computing the row-reduced echelon form, and extracting the right half of the result of that operation, which we are doing here for INV test 1, and here for INV test 2. In addition to linear algebra, we can also perform statistical operations using NumCPP, all of which can be done row-wise, column-wise, or by using the matrix elements in a flattened manner. Simply put, by using the axis rules for a matrix. We can compute the median, which is either the middle number of a ordered matrix containing an odd amount of numbers, or the mean of the two middle numbers. Or the mean of the two middle numbers of a sorted matrix containing an even amount of numbers. So in this case, the rules for an even number of elements in the sorted matrix apply here, and the rules for a matrix with an odd amount of numbers apply here and here. We can compute the mean, which is done by adding together all of the matrix's numbers and dividing the sum by how many numbers we are working with. We can compute the average, which is done by adding together the products of the matrix elements and their corresponding weights, and then dividing by the sum of the weights. We can also compute the standard deviation, variance, and peak to peak of a peak to peak, which is basically the maximum value minus the minimum value of a matrix, and the user specified percentile of a matrix. And finally, we can use NumCPP to sort a matrix, search for elements in a matrix that meet certain criteria, as well as count the number of elements that meet certain criterion. All of this can, once again, be done either row-wise, column-wise, or by using the matrix elements in a flattened manner. There are 4 sorting elements we can use, as shown here: the quick sort, the merge sort, the heap sort, and the tim sort. We can use argmax and argmin to find the indices of the maximum and minimum elements in a matrix, respectively. We can use nanargmax and nanargmin to accomplish the same tasks as the regular functions, but while ignoring non-number values. We can use non-zero to obtain both the row and column indices of a matrix of the elements in the matrix that are not equal to 0. In this case, 0, 0, 1, 1, 2, 0, and 2, 1. We can use flat non-zero to obtain the number of elements in a matrix that are not equal to 0. In this case would be 0, 4, 6, and 7. We can use count non-zero to count the number of elements that are not equal to 0. So in this case, 1, 1, 2, 2, 2, 0, and 1, 2, 3, 4. Finally, we can use the where function with a matrix containing Boolean elements and matrices of numbers containing values for when the current element in the Boolean matrix is either true or false, which is what we are doing here. And that concludes this demonstration of NumCPP. I hope you enjoyed this, and thanks for watching.